Okay, this is going to be our fourth and final video in our series on uniform circular motion. We're going to change gears a little bit in this video, and we're going to be talking about Newton's universal law of gravitation. And so far, whenever we've been talking about gravity, gravity's been an acceleration for us, right? We take gravity, and let's say, for example, in our kinematics equations, like we see here in equation 1, we simply take gravity in when we're talking about the vertical direction, and we substitute it in where the acceleration was in our horizontal direction, right? Or in other cases, let's say when we were talking in terms of dynamics in chapter what would it have been, chapter 4 and 5, we simply insert gravity in when we want to calculate the weight of an object, right? So Newton's second law tells us force is equal to mass times acceleration, and so weight is just equal to mass times gravity, or gravitational acceleration, right? And so we're now going to take a little bit of a deeper look into the sort of nature of the force that causes this gravitational acceleration. And so we're gonna look at Newton's law of gravitation. We're going to find that gravity is always attractive. We're going to find that well, basically, we're going to find that the force of gravity is given by this equation here. The force of gravity is going to be proportional to the product of the masses and inversely proportional to the square of the distance between these two masses. And this is all going to be scaled by a constant of proportionality, g, which we're going to talk about in a second here. Okay? And so let me just draw a little picture here. Let's say we have some object of mass m over here, and some other, let's say a larger object of mass m over here, capital M. And usually this is how we'll label things. The capital M will go for the larger object when we're talking about two objects that are attracting each other gravitationally, right? And so let's write the center of mass in for each of these objects. So this dot is meant to represent the center of mass. And let's draw a line connecting these two objects, connecting the centers of mass of these two objects. If the length of this line is r, then basically we have all the variables that we need to calculate our force of gravity. So F is equal to capital G, which is this constant that we haven't discussed yet, but we will in a second. M is the mass of the lighter object. Capital M is the mass of the heavier object. And r is our distance between the centers of mass of these two objects. And this basically gives us the force, the magnitude of the gravitational attraction between these two objects. Okay, and so we talk about that here, and now we write down a numeric value for our capital G. So capital G is actually 6.673 times 10 to the negative 11 Newton meters squared over kilograms squared. And we need those units so the whole thing works out. We may talk about that in the future as far as dimensional analysis goes, but for right now, this is the G that we need. And if we have lowercase m, capital M, and r, which are defined in my drawing here, we know what G is. G is just a constant. It's always the same everywhere. So if we have all those values, we can calculate what F is, and F is the magnitude of this gravitational attraction. Okay, so let's do an example here where we take a look at how this kind of plays out. This is kind of a fun example here. So the gravity between the Earth and the Moon supplies the centripetal force that makes the Moon follow a curved path around the Earth. We want to show that this is the case, okay? And so really, what do we want to do? We want to find the acceleration due to the Earth's gravity at the distance of the Moon. Okay, so let's start out part 1. We want to start out by finding, maybe I'll write this out. Find the acceleration due to Okay, so we want to find the acceleration due to the Earth's gravity at the distance of the moon. Okay, so what we're looking for is the force of gravity of Earth on moon, and I'll label it that way. Okay, so what is this going to be equal to? Well, we can use Newton's second law right away. We know that that force is going to be equal to mass times acceleration, and our acceleration here, well, our acceleration is going to be g, right? Because that's the acceleration that the Earth is going to be causing on the moon here, and it's also equal to, well, we just talked about this equation up here. So we have this equation up here, up here, and so we know that this force is also going to be equal to capital G m, which is the mass of the moon in this case, m, capital M, which is the mass of the Earth in this case, and r squared, where r squared is the distance between the center of mass of the Earth and the center of mass of the moon, right? We can cancel our m's here because these are both the mass of the moon. And what does this give us? Excuse me. This gives us g, or lowercase g, is equal to capital G, capital M over r squared. And at this point we would need numbers for these, so we would look this up. And what would we find? Well, we would find that, maybe I'll write these down. Well, we know what this constant is, right? We know this is 6.67, we'll just call it, times 10 to the minus 11. I won't write the units in there. And then the mass of the Earth is what we would need for our top m. And I'm going to write that in here. That's going to be 5.98. What is it? Times 10 to the 24 kilograms. And we also need the distance from the center of mass of the Earth. So basically the distance from the center of the Earth to the distance from the center of the Earth to the center of the moon. And that is 3.84 times 10 to the 8 meters. And again, I didn't want to include these units here, so I'll get rid of the units. But basically those are the numbers. This mass of the Earth and distance from Earth to the moon thing, you'd have to look these up, right? Like you wouldn't be expected to memorize these things. If you did the calculation, you would find that this gives us a g at an acceleration at the distance of the moon, which would be equal to 2.70 times 10 to the minus 3 meters per second squared. Okay, so that's what we find our gravitational acceleration due to the Earth's gravity at the distance of the moon is. Okay, so that's one part of what we're looking for here. We're going to see why we calculated this in a minute. It may not be immediately sort of obvious why we bothered to calculate the acceleration due to the Earth's gravity at a distance of the moon, but we'll see here in a second. So part 2, that's terrible. There we go. Part 2, we are going to want to calculate, well, we're going to want to calculate the centripetal acceleration, which we know is equal to v squared over r, which we also know is equal to r omega squared. And in this case, we're going to use the second equation. So we want the centripetal acceleration that's necessary to keep the moon rotating around the Earth, right? And so, what do we know? Well, we wouldn't know this, but we would look this up. We can find a value for the time Okay, so we can find a value for the time it takes for the moon to go around the Earth, and if we look for that, we would find that that is 27.3 days, right? But we want to be able to write things in terms of omega, right? We want our angular velocity here to be given to us in radians per second, not radians per days. So we need to do some multiplication. So the delta t that we're going to want here, and this is because we know, maybe I'll take a step back here. We know that omega is equal to delta theta over delta t. Delta t is going to be equal to, well, it's going to be equal to 27.3 days, but we want to get the number of seconds, right? So we need 24 days or 24 hours in a day times 60 minutes in an hour times 60 seconds in a minute, and this is going to end up giving us a delta t equal to 2.36 times 10 to the 6 seconds. Okay, it's an intermediate result that we're going to need there, and we know that we want a delta theta equal to 2 pi radians, right? So 2 pi. So let me go down a little bit here. If we then calculate what omega here is, this is going to give us an omega equal to, well, 2 pi radians over the 2.36 times 10 to the 6 seconds, which, if you do the calculation, is going to give us an omega equal to 2.66 times 10 to the negative 6 radians per second. Okay? And so what do we have here? Well, we have our omega, and looking at the equation from above here, we can grab our centripetal acceleration, which is just going to be this value here. Well, we just calculated omega. So, well, first we'll start off with the radius, which we had from above. We would have had to look up. That was 3.84 times 10 to the 8 meters. And then we have our value of omega here, 2.66 times 10 to the minus 6. But this one comes in squared, right, because omega here is squared. So if we did that calculation, we would find that the centripetal acceleration is equal to 2.72 times 10 to the minus 3 meters per second squared. Okay? And so what have we found here? We found that the gravitational acceleration due to the Earth's gravity at the distance of the moon was 2.7 times 10 to the minus 3 meters per second. And we found that the necessary gravitational acceleration, or at least the necessary centripetal acceleration, which can only be supplied by the gravitational acceleration in this case, would need to be 2.72 times 10 to the negative 3 meters per second squared. So these numbers really should be the same, right? Because we know that only the Earth's gravity is supplying the centripetal acceleration needed for the moon to stay in orbit around the Earth, and we just calculated what that value should be. So why are these different? Even though they're very close to the same, they are a little bit different. Why are they different? Well, they're different because we've made an oversimplification here, right? We've taken the distance, this distance here, we've taken that to be the distance that these objects are rotating around. In reality, they're rotating around their common center of mass, which is not quite the center of the Earth, but it's a little bit off center of the Earth, still under the Earth's crust, but a little bit further out. So we'd have to adjust these, and if we made that adjustment, we're off by about 1% here. If we made that adjustment, we would find that these actually ended up agreeing to a much better degree. Okay, so that's one example of how we might use this idea of Newton's universal laws of gravitation, right? Okay, so that's basically all that we've got for this chapter here. The text does go on to talk about a few more things. The text talks about how the moon's gravity has effects on things on the Earth, tides, etc. We're going to skip that section. It also talks a little bit about black holes devouring stars and things like that. Those are all very interesting topics, but there's no new physics sort of introduced there. I mean, those are topics that a lot of physics could be used to to look at, but there's no new physics in the text where they're talking about it there. Things would get a little more complicated if we wanted to go down that path. So we're going to skip that section. The text also goes on to talk about Kepler's laws. We're not going to discuss that in this course. You guys should just be aware that it's in the text. If ever you find you need it, it's there, and you do have all the tools you need to sort of work with that at this point. But we're not going to talk about it in this course, so you guys won't find any questions on that on any of the assignments or in any of the tests. Okay.